Okay, welcome back. I'm delighted to introduce our next speaker, Ramos of Stevens Institute of Technology. He'll talk about Robertson's conjecture in topological combinatorics.
Okay, hello everyone. Well, first of all, let me thank the organizers for inviting me to speak here. It's really quite an honor, so thank you all. Yeah, so today I'm going to talk about Robertson's conjecture in topological combinatorics. I was warning the organizers before my talk that I don't know, I've not given many 20-minute talks, and so this might go under, which is great because it's right before lunch. So we'll see. Okay, so yeah, so let's get started. So we say that a graph. Oh, by the way, if my mic, if I'm not talking properly and my mic doesn't pick it up, please somebody tell me. So we say that a graph G is a topological minor of a graph G prime if a subdivision of G is isomorphic to a subgraph of G prime. And we're going to write the usual G less than or equal to G prime to denote this. So as a picture, here's this. So the idea essentially is like, okay, so on the left you have a triangle. That's great. Topologically, a triangle is basically a square. So like the square that I've drawn kind of in the middle there, it's like, basically. So yeah, so you see the square on the right is a subgraph of the big graph. And the triangle, if you subdivide it, you get the square. So this is kind of how the relationship here works. Oops, wrong way. Okay, so one of the great early triumphs of topological graph theory is Kuratowski's theorem. And just so we're clear, a graph can be embedded into the plane, i.e. is planar, if and only if neither K5 nor K33 appear as a topological minor. In other words, containment in the topologically minor closed family of planar graphs is decided by a finite list of forbidden minors. Okay? So it's a problem that's decided by a finite list. Now, some of you, maybe most of you, probably all of you, know this thing called the graph minor theorem. So there's a different notion of just graph minors. And for graph minors, it's about deletions and contractions of edges. And the graph minor theorem, which proven by Robertson and Seymour, says that if you have any minor closed family, it's always decidable by a finite list of forbidden minors. So the question then, the natural question, is it the case that all topological minor closed families are similarly determined by a finite list of forbidden minors? Or in more technical terminology, is this ordering a well quasi-order? So that's the question. Turns out the answer is no. And not only is the answer no, it's not even one of these things that you construct it using the axiom of choice in some weird way. So here is a family for which, so let me kind of explain this. So here's a family. So you imagine taking a triangle and putting kind of 3 little tendrils off the sides there. And then the next thing is you take 2 triangles overlapping at a vertex and do the same, and then 3 triangles in sequence. So imagine taking the family of all graphs which do not have any of these as a topological minor. So by definition, that is a minor closed family, right? If I don't have it as a topological minor, then none of my topological minors will have one of these as a topological minor, right? But the problem is that within this infinite family, there is no, like, oh, one of them is a topological minor of the other. So in other words, like, if you imagine the minor closed family of graphs that do not have this as a topological minor, this cannot be classified by a finite list of forbidden minors, because this infinite list, you would never find like one thing that's inside the other. So this kind of breaks it. Button. Okay, so it was observed by Robertson, which is the same Robertson of the Robertson-Seymour graph minor theorem. It was observed by Robertson and others that many counterexamples to the well quasi-order property were built out of chains of triangles in a similar fashion. Okay. So just to draw this picture again, like the idea here is that you have a chain of triangles and then you tack something onto the ends so that like you get this weirdness where one never embeds into the next. So we call such chains of triangles Robertson chains. Okay. So very recently, Leo and Thomas proved a conjecture of Robertson that made this observation precise. So just a very quick sidebar, which is like, the graph minor theorem was proven over the course of 20 years and about 20 papers. The first of which is called the theory of graph minors, part 1, and the 20th of which is the theory of graph minors, part 20. So when I say that Leo and Thomas proved the conjecture that I'm about to show, what I mean to say is that the paper, Robertson's conjecture, part 1, has appeared on the archive, and I guess we'll have to wait 20 years for the rest of it. So Robertson's conjecture states the following. Let GD denote the class of graphs which do not contain a Robertson chain of length d or higher as a topological minor. So let's break for a second. So G1, this says we do not have a Robertson chain of length 1 as a topological minor. What is a Robertson chain of length 1? It's a single triangle. Okay? What does it mean to not have a single triangle as a topological minor? Well, what it means is that I'm a tree. So G1 is the class of trees. Okay? G2 is going to be the class of graphs for which you can never find kind of two triangles kind of touching at one of their vertices, and so on and so forth. Okay, so as a topological minor. Then containment in any topological minor closed family within GD is determined by a finite list of forbidden minors. Yeah?
Which Leo, which Thomas?
This is Chunhung Leo, who's at Texas A&M, and Robin Thomas. Yeah. Okay. So next, okay, so yeah, this is Robertson's conjecture. As I said, this is Robertson's conjecture in the same way, that Sayre's conjecture is a conjecture, which is to say, at this point it's been proven, but probably we're going to continue to call it Robertson's conjecture. So yeah, this essentially has been proven. Okay, so next we move on to an object of importance from topological combinatorics, which is graph configuration spaces. All right, so let G be a graph thought of as a one-dimensional topological space. Then the n-pointed configuration space on G is the topological space. So I want to think about n tuples of points on G with no overlaps, right? Xi is not equal to xj. Unless I is equal to j. And I want to mod out by the symmetric group action. So notice that if I have such an n tuple, the symmetric group acts by permuting points, right? Permuting coordinates, sorry, to be more precise. And that's like a nice, properly discontinuous action. And so like this thing is a nice quotient. So this is kind of what I'm going to call the configuration space of points. Okay. So these spaces, so when people talk about configuration spaces, they're usually talking about things based on work, say, going back to Arnold, which is like configuration spaces of higher dimensional manifolds and varieties and stuff like that. And that's like a really beautiful theory and et cetera, et cetera. Thinking about configuration spaces of graphs is something that, was not really a big thing until the early 2000s. And a lot of the early push was coming from, like Robert Geist, for instance, thinking about like applications of topology. So, when I say applications to topological robotics, you can imagine like, building tracks, right? And you have robots moving around in a factory, and they're only allowed to move along predetermined tracks and stuff like that. And you don't want the robots to collide with one another. So this is a natural way to model that. Okay. So this is graph configuration space. Okay, so what is going to be relevant to us is the following list of theorems, each of which points to some kind of underlying uniformity across all graphs. So let's start with the first one. So uniform boundedness of torsion. So this is by Coe and Park. For any graph G, the largest torsion appearing in H1 of Fn, for any n, has order at most 2. Okay. So across all graphs, if I look at H1, no matter how many points I'm configuring, If I look at H1, the torsion has order at most 2. In fact, you can go beyond this. The actual theorem of Cohen-Park says that the question of whether or not my H1 has 2 torsion is exactly the question of whether or not I am planar. So basically, 2 torsion appears if and only if G is non-planar. So that's kind of cool. OK, number 2, universality of generators for trees. This was essentially done by Farley. So if G is a tree, and I and N are at least 1, then the ith homology group of Fn is generated by products of H1 classes pushed forward along embeddings of star trees into G. So what is a star tree? A star tree is literally just the tree, which is a single vertex and a bunch of edges coming off of it, right? So the idea is like, OK, a tree is built out of these stars being glued together in some way. And so you can imagine, like, oh, what's happening locally around this kind of star, and you embed those classes into your bigger tree, and those things will generate all of HI. OK. Interesting. Next one, universality of planar generators for H2. So this is a much more recent result due to Ahn and Knudsen, Ben Knudsen. So universality of planar generators for H2. So there exists a finite set of graphs, which I can tell you what they are, but, well, whatever. A finite set of graphs depending only on n, such that for any planar graph, H2 Fn of G is, oh, sorry, yeah, no, that's right. H2 Fn of G is generated by push forwards of classes along embeddings of the members of this finite list into G. Yeah. Oh, n? Yeah, so n is just, yeah, you're right, bigger than or equal to 1. Yeah, thank you. OK. OK. But the business about having torsion if and only if G is planar doesn't apply to the n equals 1 case. Because n equals 1, you're just looking at the graph itself as a topological space, which is not going to have torsion. Yeah. OK. All right. So here are like extremely, universal and kind of, I don't know, extremely nice theorems, all of which point to some underlying mechanism here that's causing some behavior that you might not expect. OK. Yeah. So let's just take a second to take stock of what we have. So fix for now an integer d. And suppose we are working only with graphs not containing Robertson chains of length longer than d, i.e. we're living inside of this GD. Well, notice that if G is a topological minor of G prime, then for any n, there is a natural continuous map from configuration space on endpoints of G to configuration space endpoints of G prime. As I said, the whole point of the topological minor relationship is essentially what I'm saying is like G, thought of as a topological space, embeds into G prime. So there's just going to be a natural kind of continuous map here. So these maps at the level of topological spaces, as continuous maps usually do, will induce homomorphisms at the level of homology groups like this, as such. So I don't think I'm saying anything kind of extreme here. So at this point, though, we kind of find ourselves, as I said, in kind of the realm of categorification. So it's kind of a scary word, but it actually has a very simple, I don't know, motto, which is like anytime, I think of it, anytime you have an integer, that integer is secretly the dimension of a vector space. Okay? To me, this is what categorification is. And that vector space, the algebra of that vector space, is somehow encoding the combinatorics that you started with. So let me give the following definition. So a GD module. So I'm going to call, for any integer d, a GD module is a collection of abelian groups, VG, one for each graph in GD, such that whenever G is a minor of G prime, there is a natural homomorphism from VG to VG prime. Okay? So it's just literally a collection of groups, one for every graph. And whenever something is a minor of the other, you get homomorphisms, right? OK. So we say V is finitely generated whenever there is a finite list of graphs, G1, G2, et cetera, such that for any graph G, Vg is spanned by classes coming from the groups Vg prime. OK. All right. So this is what I mean when I say a GD module. All right. So this is now the categorical Robertson conjecture. Now this one is still a conjecture, for real. Except for d equals 1, we proved it. But for all higher d's, this is still a conjecture. And it states the following. For any integer d greater than 1, if v is a finitely generated GD module, then all submodules of v are also finitely generated. Now, I didn't explicitly tell you what a submodule was, but I think you can guess. It's just like, again, if a GD module is a collection of groups with these natural maps, then a submodule is just a collection of subgroups for which the maps just restrict in the natural way to be the maps. OK. So if you take a finitely generated thing, then the submodules are finitely generated. So this might seem like really abstract and totally out of reach, but I'll just say that other well-known well-quasi-order theorems have been categorified in a similar fashion, including Kruskal's tree theorem, which was done by Daniel Barter, and independently myself and Nick Proudfoot, and even kind of a weakened version of the graph minor theorem, which was done by myself and Dane Miata. So finite generation of graph configuration spaces. So if this conjecture is true, then we can prove as a corollary for any integers di and n, the GD module, which gives you the homologies of these configuration spaces, is finitely generated. Okay. Now again, the whole spirit of finite generation is that there is a finite list of homology groups for which if you allow yourself to push forward things from that finite list, you get everything in all other graphs all at once. OK. So supposedly this is my last slide. So this, as I said, this would be the main corollary coming from this kind of categorical Robertson's conjecture. But now you say, OK, this is kind of awkward because we have this dependency on this D here, which is basically telling me the biggest Robertson chain that appears. But in all of the theorems we looked at before, there was no except for the one on trees, but other than that one, there was no dependency on this parameter D. So, well, what's going on here? So the idea is that if you vary D, you get kind of a filtration of these homology groups as you kind of allow for more and more graphs. You're kind of embedding one into the next, into the next. And this filtration actually stabilizes, in a sense, over time. And the reason for that is kind of a categorical version of the graph minor theorem. It's going to have to stabilize over time. So you do get this kind of dependency on D is not that big a deal. And so as you get from this kind of finite generation statement, all of the theorems that we saw before are essentially shadows of this. Okay? This finite generation is telling you that a finite amount of algebraic information coming from a finite list of graphs is determining what all of these graph configuration spaces are doing across all graphs. Okay. All right. Yeah, okay. No, that was basically all I had to say then. All right. Well, thank you.
Questions? Yes.
Yeah, so are there any instances that you know of where you have sort of a kind of, let's say classical version of this that ends up being true that, present the categorical rotation that's false, i.e. that there are no infinite, well, quasi-order means no infinite entities, right?
Yes, that is correct.
In other words, there's no infinite anti-chains, but then when you go to the categorification, things are infinitely generated. Or are there instances you know of the other way around happening, or is that even possible? Is there an implication one way or the other?
Yeah.
And repeat the question.
Yes. So the question was, are there, just in a general sense, are there famous examples of well quasi-order theorems for which the natural categorification is false? And conversely, are there cases where the categorical version is true, but then the traditional version is false? So the first thing I can say is that like if it is the correct categorification, it will imply the original theorem.
Oh, I see.
Yeah. And the way that you see that is like, for instance, in this case, here's a GD module assigned to every graph just Z. Okay. And for every topological minor relation, the induced map will just be the identity. Okay. Okay. So now take with it. All right. So that's my original module. That thing is clearly finitely generated just by a single point, because like the data of like that will propagate outwards. Now, if instead you take a class of graphs which is topological minor closed, you can define, well, I'm going to anything in that, to any graph in that class I assign Z, and to all other graphs I assign 0. And the maps are the identity once again, or the 0 map depending. So the second thing is a sub of the original thing. And so if you have the categorification, then that sub is going to be finitely generated. And then the kind of generators of this sub is going to be the finite list of forbidden minors that you're looking for. So the categorification should imply the original theorem. Going the other way, so are there examples of famous WQO theorems whose natural categorification is false? Actually, not really. The categorification, this particular categorification project has been quite successful in that sense. A lot of it is based on machinery due to Stephen Sam and Andrew Snowden. They call it like Grubner categories. And yeah, it's actually been quite successful in that sense. Yeah, so, yeah. Mm-hmm.
Other questions? Yeah, Arun.
So I actually have 2 questions.
Yeah.
The first one is, for given a D,
Yeah.
do you expect there to be a universal finally generated?
Repeat.
The question was, for a given D, do I expect a universally finitely generated object? What exactly do you mean by that? Could you explain?
I don't know, I'm looking for the universal object, which is capturing the GD structure.
He's looking for the
Universal object, yeah. Capturing the GD structure, thank you. Sorry. Okay. I guess in the way that I guess the closest thing, so what I said before, which is this, you can imagine like the GD module, which is like literally, you assign to every graph just Z, right? Like this, in my mind, like in some sense, like the way that I think about this, if you want to kind of think back to like modules over rings, like this thing is the ring itself being expressed by a module. So like to me, that object is universal in that sense. Yeah.
My second question is, how big are the kernels?
So the question is, how big are the kernels here? Kernels with respect to what maps?
Well, you've been finally generated, but the homology itself is going to be a huge quotient.
Yes. So
Homology itself is going to be a huge quotient.
Sorry. Okay. So right. So the homology, like. So let me try to understand the question here. I apologize. So when you say quotient, in what sense do you mean? Like,
I've
yeah.
chosen some favorite generator.
Yeah.
And they're going to generate my ith thing.
Yeah.
But that ith thing will be the generator's modulo of
I see what you mean. Okay, so you're asking like how? Okay, so so we have some, because hi here is finitely generated. It is by definition the quotient of like some kind of free object, and the question is like how big is the kernel of that quotient? Yeah, so that's a great question. So the thing is like, again, this theorem, for instance, is a corollary to a categorical Robertson's conjecture, which you can think of as like the Hilbert basis theorem, right? So like we get finite generation as an abstract consequence So even understanding the generators is something that I would, as a starting point, was something that I would really like to do. In the
But we should wrap it up.
oh, okay, wrap it up. Okay.
And you guys can talk later.
Yeah, we can talk later. Like these theorems, we have explicit generating sets, but outside of these theorems, we don't at all. So like even getting the generators would be a great step forward. I'll just say that. Yeah.
Before we thank the speaker again, I want to say that at noon there will be a big announcement. So don't head off to lunch just yet. But let's thank the speaker again.